Hi, my name is Rick, and today I'll present to you our paper titled MorphPool, Efficient Nonlinear Pooling and Unpooling in CNNs. The paper was written by Leo Dorst, Theo Gevers and myself of the University of Amsterdam. In this presentation, I'll walk you through our paper, our method, and our experimental results. But first, I would like to start with a motivating example. We observed that there exist many up and down sampling schemes in neural networks, more specifically encoder-decoder networks. These networks take high resolution, high frequency input and downsample to a set of low dimensional but expressive features in their information bottleneck. From this set of features, the network upsamples again to obtain a full resolution output. Sampling can happen in a variety of ways, but it's good to note that it's always a pair in encoder-decoder networks. On the bottom right of the slide is a schematic of a network we're interested in. The down and upsampling layers are highlighted in blue and yellow respectively. Those are the layers that we target in our paper. For example, when sampling linearly, the downsampling operation of choice is a strided convolution, and the associated upsampling operation is then the linear transposed convolution. In practice, people choose to use a static interpolation scheme, something bilinear or bicubic. When pooling is used as the downsampling operation, the associated prevalent method in literature to upsample is a combination of unpooling and a transposed convolution. The reason transposed convolution is used is because unpooling introduces zeros, the sparsity, in the feature volumes. And the transposed convolution is a rather ad hoc method to linearly interpolate and deal with the sparsity. This issue of sparsity is shown on the bottom left of the slide. Because of this, we ask ourselves two questions in our paper. Is MorphPooling a member of a more general family of operations? And if so, does that mean that there is also a naturally associated upsampling operation that could replace the combination of nonlinear sampling and linear interpolation that is now the unpooling transposed convolution combination? Let's start with the first question. It can in fact be shown that MorphPool is a non-parameterized, non-overlapping special case of the morphological dilation. The dilation is one of the fundamental operations from mathematical morphology, and the field of mathematical morphology was founded by Jean Serrat in the 1960s. First developed for sets and binary images, but later extended to grayscale images and also general images. Nowadays, people actually use mathematical morphology to build neural networks called morphological neural networks. In addition, morphological layers could be integrated in CNNs, which is what we're interested in this paper. MorphPool is a discrete local strided maximum operator, shown on the middle of the slide here, with stride S, actually always 2, and Z, the indicator set over the local neighborhood, which actually also always is a 2x2 patch. Through some algebraic manipulation, we show that this operation is actually a special case of the morphological dilation, as is shown on the slide here on the bottom, with some flat structuring element or kernel called H. Now this structuring element H is quite useful because we can parameterize it. For example, we can let it be parabolic, in which case we can construct morphological scale space through the MorphPool, or we can let it be a general kernel, in which case it's more similar to a convolutional kernel. And here's what that looks like visually. On the left we've got the morphological pool, the generalized MorphPool, and on the right we've got the morphological unpool, which is the associated upsampling operation, which I'll discuss in a minute. So to start on the left, we've got a 5x5 image patch, and we're tasked with downsampling it by a factor of 2. Unlike MorphPool, we're free to use a 3x3 overlapping set of windows, which is what we'll do. And for simplicity's sake, I've chosen to keep the structuring element H completely flat, similar to what you would do in MorphPool. In fdown, we record the set of maximum values, and in addition, we also store the location of the maximums in a variable z, which we call the provenance in the paper. On the right is the two-stage upsampling procedure, morphological unpool, which consists of morphological sampling and morphological interpolation. Starting from F down, we put back the max values at their respective locations using provenance set, and we fill all non-maximum elements with minus infinity. The tropical algebra of morphology allows for the use of minus infinities. In regular unpooling, we would fill these elements with 0, but that is because we then linearly interpolate between the elements. Here we morphologically interpolate between the elements, and therefore minus infinities are required. In our second stage, we do this morphological interpolation, and practically that means we have to apply dilation, but rather with a larger 5x5 structuring element to ensure that we completely suppress all minus infinities, simply because the linear components in our network would not be able to deal with minus infinities. And now that you've seen an example, I will formalize our unpool. The goal of morphological unpooling is to invert as much as is possible the morphological pooling operation. However, full inversion is not possible because morphological pooling suppresses non-maximum elements through the dilation operation. And this is why morphological unpooling is a two-stage process. So in the first stage, we place back the maximum values by means of the provenance, which in the previous slide was called Z. And for all remaining elements, we impute a value minus infinity. We argue that these values minus infinities can actually be filled using the upper bound of the sparse values, so the placed back values, by means of a morphological interpolation, so dilation again. This second stage can be parameterized, just as the morphological pooling could, by a kernel or structuring element H. So again, we can make use of all these useful concepts from mathematical morphology. Let's look at some results. In this table, we compare the performance of MorphPool to two other sampling schemes. Linear, which is a downsampling by strided convolution and upsampling using interpolation, and standard pool, which is downsampling by pooling and upsampling by unpooling in combination with transposed convolution. The networks were fed with depth maps for both a semantic segmentation and depth autoencoding task. In the second column, we denote the amount of additional parameter required by the methods. In the third to fifth column, we denote performance on the semantic segmentation task, and note especially the fifth column, in which we denote the boundary F1 scores, which measures the performance at semantic boundaries. And in the sixth through eighth column, we show the performance on a depth autoencoding task. From these results, we can see that consistent inversion, either linear or non-linear, seems to outperform a mixture captured by the standard pool. In addition, MorphPool outperforms linear sampling for this particular data. We hypothesize this is because depth maps are nonlinear at geometric edges, and linear sampling would smooth out edges and structure. We can see this in the boundary F1 score on semantic maps, in which we want clearly delineated object boundaries, but also in depth autoencoding, in which MorphPool just generally outperforms linear methods. Finally, note that MorphPool generally has much fewer parameters than its linear counterpart. Even when fully parameterizing the MorphPool operation, we only have about 70k parameters versus the 30 million parameters that is introduced by a fully linear interpolation scheme. Let me summarize the presentation. Max pooling was shown to be a non-parameterized, non-overlapping special case of the more general morphological dilation. The advantage here is that this dilation can be parameterized by a structuring element H, making the operation much more expressive. In addition, there is an associated upsampling procedure that we call morphological unpooling, which can replace the unpooling infilling scheme that is currently used in literature. This makes the entire procedure fully morphological. MorphPool can increase performance at much reduced parameter counts, and this effect is most pronounced on depth data. We think think this is the case because morphological operations can preserve edges and structure, and in the case of semantic segmentation, it can delineate semantic boundaries. In this sense, mathematical morphology appears to be the natural language to express nonlinear geometry from virtual contact probing. Thank you for watching this presentation. I invite you to read our paper for more details, and also we make available our code, which can be found at the link below. Thank you very much.